Let's see where to start. Stoichiometry, that's easy. And just bust out chapter 5 really quick. Let's say we had a reaction as such, which this is a neutralization reaction. And let me write the product. Okay, and I would want to balance as well. 2 there. I think 2 water should do it. Okay, it's pretty common for a titration. So the keywords would either be titration, neutralization, or standardization. All those mean the same thing. It means it's a stoichiometry problem. You would note it by a reaction happening and a molarity being in the question. So let's say this was 1.0 molar and 2.0 liters. Let's say this was 1.0 liters, and I wanted to know the molarity of this one. That'd be a pretty classic question. You also notice we only ask you about reactants and not about products. That's also a classic titration problem. So you're going to do your 3 steps. You're going to start here, change to moles. You're going to do a molar ratio to go here, and then you're going to solve for what we want. In this case, we want molarity, which is moles per liter. So let's try that down below. So start off with what we have. We've got 2 liters, and we've got 1.0 molarity, which is moles per liter. So I want to convert to moles right off. Second step, I want to use my molar ratio to go to what I want. 2 moles of NaOH for every 1 mole of H2SO4. Okay, so that's my molar ratio. Last step, I want to convert to what I was asked for. Right now, if I do all the canceling, liters are gone, moles of sulfuric acid are gone, and I've got the moles of the sodium hydroxide. So I'm actually halfway there. I want moles per liter. What volume do I use here? Yeah, the actual 1 liter. Okay, it's not asking for the total volume, so I'm actually going to divide by the 1 liter. And this total amount, which, get your calculator out, but I think it's 4 molar, would be your final answer. So it's a pretty classic titration question. They don't really get harder or easier, except we use different terms. Titration, standardization, etc. So that's that. No questions? We're moving on to chapter 6 now. Or gases, yes. Some people use the following equation. I know some of your TAs are into it. I'm not totally into it. The reason is this right here. That molar ratio, if it's not 1-to-1, doesn't work here. So you have to pop on an extra calculation. So if that keeps straight in your head, that's fine, but technically this is dilution. So I prefer this sort of calculation. But yeah, if you have a style of doing it that's different, that is chemically correct, that's okay. Let's go to chapter 6 then, or the gas chapter. Yes?
What were the keywords again?
Keywords for this problem: titration, standardization, or neutralization. All those words would basically mean the same thing. You also recognize it by all the calculation has to do with the reactants only, and you'd also recognize it by molarity being in the problem. Okay, next. Let me do a few gas things before I get to the overview. Let's start with Graham's law. Okay. Graham's law says that if you have a property of gas A over the property of gas B, that equals the inverse of the square root of the molar masses. Oops, that's A. So this part here that I'm underlining never changes. What changes is what possible properties could go in here. So this could be rate or velocity of A over the rate of B. Or it could be distance. I'll put D for distance. A over the distance that B travels. So how far the molecule travels in a particular time. It could be amount, like moles, for example. Amount of A over amount of B. Or it could be time. Time's the funny one, where time is, see how most of the time it's A over B, except for time. The time that B over A matches, this. So I would give you this formula right here on the test. You'd want to know what possible properties would affect it. In a Graham's law question, let's do it for distance. Let's say we had helium, and let's say we have methane, for example. And I want to know, let's say one way to write it is I want to know the ratio of the distance traveled by helium and methane, for example, CH4. For example, that's kind of what I want, the question. The ratio means whatever's listed first, that's what I want in the numerator, and whatever's listed second, that's what I want in the denominator. One thing to make the problem extra fun that we'll toss in, for example, in this one, we could say the ratio of the distance traveled by helium in 125 seconds, say, versus methane at the same time. So the same time allotted. So in our calculation, what would we do with the time if I gave 125 seconds? Where would it appear in my calculation? Yeah, nowhere. Yes?
I'm sorry, you said amount A about the time. Why is it P over time instead of the other?
We didn't derive this. The question's about this one. I just told you it was inverse. It has to do with distance and rate being inversely proportional, like in a distance equals rate times time sort of calculation. So, but I just told you that. We didn't derive any of that. Okay. So yeah, so what can happen is, let's say I'm asking you about distance, and then I'll also give you a time. In this case, 125 seconds. But the time will be both the same for each one. Then you don't use the time. It's just saying that we're doing a consistent experiment across both. I could have also said we want the ratio of distances, and I give you the amount of both. Again, that's not important. So it's often that we'll give you an additional variable that's not relevant to the problem, but it tells you, but it's the same amount or the same number numerically for both. So the time is the same for both. It could be, if I'm asking about the rate, the distance could be the same for both, whatever. Whatever that is that's the same is not used in the calculation. It's just for fun. It's technically used to show that each part of the experiment is done consistently. So if this was asked, you would just say, well, the distance of the one listed first, helium, over the distance of the one listed second, methane, is equal to inverse to the square root of the molar masses of methane over helium. Methane molar mass is about 16. The molar mass of helium is about 4. That's going to be the square root of 4 over 2. That means that helium will go twice the distance of the methane, which is what we expect because, why would we expect that? Yeah, helium is lighter or smaller, so to go a further distance or to go at a faster rate, or in the case that was asked just a second ago about time, it would take less time to get there by half. Okay, so again, the time, even though I gave it, was not used in the calculation. Okay. It doesn't have to be time in particular. It could be any variable that's given the same for both. All right, that's Graham's law. Graham's law is technically for effusion with an E. That was one of the questions here. Effusion with an E, technically, that means escaping of gas out of an orifice or out of a hole. Diffusion is just the generic migration of particles. So even though Graham's law was derived, not by us, but by other people, but for effusion, it also works for diffusion. Okay, so it will work for both, but it came initially from diffusion. I was just asked about the definition. So there we go for Graham's law. Let's do the root mean square velocity. The root mean square velocity, URMS, is the square root of 3RT over M. It's true. Okay. This is just a plug and chug sort of formula. So you would be given really only one variable, temperature. Okay, so if you had this, For helium, as an example, all you need is the temperature. So let's pick, somebody give me a number. Oh, okay, no, too small. It'd have to be in the hundreds. 420, there we go. Oh my God, I should have, wait, what's up, dude? What are you smoking right here? All right, so let's just say with that, I should have come up with my own number apparently. 3 times this R. Remember, this R is used in all cases except for what formula? The ideal gas law, times 420 Kelvin, divided by M, which is not 4 grams per mole, but you need to change it to kilograms. It's an SI unit only question, so you want to divide by 1,000 to get into kilograms. So the key places where people make mistakes, the wrong R or the wrong M, or just can't use a calculator, okay? So that'd be the most common. It's plug and chug otherwise. If you need the velocity, it's there. There's one other velocity that I might as well do now, even though it's in chapter 7, or the electron chapter, is de Broglie. So let me mention de Broglie because it's also a velocity. De Broglie is U equals H over M lambda, or sometimes you'll solve for lambda. It's H over mu. This is technically an electron chapter, but since it's a velocity, let's talk about it now. There's really two, it's the same formula. We're either asking for wavelength or velocity, one of those two things. And so the difference between the top one and the bottom one is what you're given. If you have a wavelength, you're going to use de Broglie. If you have a temperature and no wavelength or things like that, you're going to use the top one. Yeah? That's right. It has both aspects, having the mass and technically the velocity compared to the wavelength. So usually you're going to use de Broglie if you're talking about something smaller than an atom, like a proton or an electron, something like that. Usually you're going to use the root mean square velocity if you're talking about a gas, some sort of gas, like helium, methane, xenon, things like that. But otherwise, if you totally blank out on what I just said, just see which variables you're given and use the appropriate formula. It's plug and chug otherwise. H would be given, and then one of either lambda or U will be given. What is typically the mass? This is typically done for what kind of entity? An electron. So you find the electron on the back page of the exam. Find the mass. Okay? So unless we specify otherwise, typically this is done for an electron, so you want the mass of electron right there. Okay, that was de Broglie. A little sidestep into a different chapter. All right, let's do the kinetic energy. That kind of goes together as well. Kinetic energy has two formulas. 3/2 RT, and 1/2, I'll write it the way we use it. Capital M for, what's it called, molar mass, times the root mean square velocity. Okay? So those are the two forms we typically would use. I'd recommend using this one. Let's make sure you got the concepts right. At the same temperature, all molecules will have the same average kinetic energy, true or false? True. How about this? At the same temperature, all molecules will have the same kinetic energy, true or false? That's false, because on average they'd have the same kinetic energy, or on average they'd have the same velocity, but it literally might not be the same number. So the energy or the velocity could slightly vary. But this again is plug and chug. So if I give you the temperature, if you're still into the 420 up there, it'd be 3/2 R. Again, you use this one in all cases except the ideal gas law times temperature. Okay? And then you'd get something out of that. One more thing. Why did I want a high temperature? It had to be a high temperature because
Chemicals are more ideal at higher temperatures.
that's right. Molecules tend to behave ideally not as a real gas, but an ideal gas at higher temperatures. As the temperature goes down and the pressure goes up, then it behaves less ideally. Okay, there's a couple other factors, but those are two of them. Yes?
Can you repeat the sentiment about at the same temperature compounds?
The true statement about the temperature, at the same temperature, all molecules would have the same average kinetic energy, not the same exact kinetic energy. Anybody else on this? Just plug and chug also. Okay, so you just see, what variables do I have to calculate this? There you go from there. Okay, let's go back. We just did kinetic energy. Let's do, so how do I do the formulas? Hopefully we're going to see maybe a few, well, no, that's all the formulas you have asked me about. As far as formulas, somebody up here asked me, I would see what variables do you have, and then what formula fits in. So in the worst case scenario, you don't know anything about chemistry. A number of these problems can just be done by looking at what formula fits the variables given on the back of the test. Okay? So you've seen the kinetic energy formula, the root mean square, even Graham's law. They're all really plug and chug. And that's about it. There's a couple other formulas that you learned that will be given on the back of the exam. If you have the variables for it, you know, and it asks you for energy, well, is it kinetic energy, or is it the energy from the Bohr, kind of the Rydberg equation? There's only a couple places you see energy, and you just pick the right formula. Or if it's a velocity, do they want the root mean square velocity, or am I given a wavelength, so I'll do a de Broglie velocity. So that's how you kind of decide what formula you're using, what variables are given in a given question.
Question?
Yeah?
What formulas do you need to memorize?
What formulas do you need to memorize? Very few, if none. You manipulate, but you don't need to memorize ideal gas law.
Unit conversions?
Units, yeah, that's not an equation, but units. So let's do units since you just mentioned it. It's good, thank you for the transition. Okay, you need to know that joule is a Newton meter, a Pascal is a Newton per meter squared, so I don't give you these. And a Newton is a kilogram meter per second squared. So then if I gave you something like, let's see, joules times joules over kilogram, and I said simplify, you would just plug in accordingly. Okay, that's the square root of joules a Newton meter over a kilogram. Newton is a kilogram meter per second squared times that extra meter that's right there, and then the kilogram on the bottom. Notice that the kilograms drop out, and I have now the square root of a meter times a meter, or meter squared, over second squared, which would just be a meter per second. So, simplifies down to a velocity. Okay? So, you'd want to know, and if you are bound to forget or blank out on an exam, write this in the first 30 seconds of the exam on the back page so you always have it with you. Anything that you think you would forget that you really need to remember, write that down on the back of the exam. Or if you think you would forget how the electron configuration works, like for example this stuff, you know, the first one's 3D, not 2D, or this is 2P, or if you think you'd forget N is always larger than L, whatever doesn't stick with you, but you know you need to know, write that down. It's worth the first 30 seconds of the exam, just in case you blink out later. Okay, let me say a little bit about STP. Because different books have done different things, I am going to have to specify what I mean by STP. So STP, that means standard temperature and pressure. It's always 273 Kelvin, but the pressure is either 1 bar or 1 atmosphere. I'll just specify for you. According to Zumdahl, your textbook, it uses the bottom pressure, which forces the 22.4 liter per mole conversion. But the technical standard right now is the top one, which is the 22.7 liters per mole. So I'm just going to specify, if I say STP, I'll also give you the pressure, just to be super clear. Okay? Yeah, I don't know what else to do about that. Okay, next. Or any questions? Are we doing okay? Yes. 7 is the top one. 22.4 is the bottom one. Okay? Next. Let's do the partial pressure. This is Dalton's law. There's two sorts of questions, and if you have a specific example, you can show me afterwards. One type of question, so two types is generically what you're going to see. One type is if you have two gases, so you have gas A and gas B, and say they're separated, and then you remove the separation and they start to mix together. Okay? And I will usually give you, you're given, say, the mass or the moles of A and B. And so what you'd want to do is find the mole fraction of both of them. For example, A would be the moles of A over the moles of A plus the moles of B. And then you'd find the mole fraction of B, which would be the moles of B over the total moles, moles of A plus moles of B. And after that, you would say, okay, the partial pressure of A is the mole fraction of A times the total pressure. There's two ways to get the total pressure. Either the total pressure is given, or you find it, if you're doing it the method I tend to do it, through the ideal gas law. P equals nRT over V. So either a total pressure will be given, or you need to use the ideal gas law to find it. Let's back up for a second here. Either for these givens here, either the mass is given, and you use the molar mass to get to moles, or we could straight up, the easiest possibility is give you moles, or I could give you, you'd find the moles, maybe I should say it that way, PV over RT, meaning I give you pressure, volume, and temperature, and you just have to use the ideal gas law to find moles. So there could be a number of ways that the givens work, but the method of solving is going to be the same. There's another style, or another type, I call over water. Really, the key preposition is over. So, over, and this is, I don't think we did an example in class, but I will show you in the reader. This was covered at the very end of the gas chapter, somewhere, on page 60. It could be over other substances as well, but in this case, over water, just as an example. So in this case, you're collecting something over water. So there's kind of two parts to this. One is that when you're collecting something over water, the total pressure is the pressure of gas that you're collecting, partial pressure of gas, plus the vapor pressure of water over which you're collecting it. So that's one key formula you use. Let me go through all these variables for you. The total pressure is usually, or almost always, atmospheric pressure. So if you're working in atmospheres, it'd be 1 atm. If you're in torrs, it'd be 760, etc. Atmospheric. The pressure of the gas is typically what you're solving for. Does anybody know where to find the pressure of the water? Yeah, it's going to be given on the back of the exam in a table that I'll show you. Looks like this. It'll say vapor pressure of water at various temperatures. I'll give you one of these temperatures and you just read off the vapor pressure of water. Okay, it says vapor pressure, that's the same as partial pressure of water. So this is from a table. P gas is usually what, oh wow, that's really big. P gas is usually what you're solving for. P total is usually atmospheric pressure. So then there's one other formula that you're going to use, which is the ideal gas law. And this was a certain form of it, the partial pressure of the gas and the moles of the gas. So typically, I'll circle this, if you find the partial pressure of the gas here, you plug it in here, and then you're going to usually solve for the moles of the gas. From there, if we ask for mass, you can convert moles to mass. But that's typically the Dalton's law part of the problem, is going to use those two equations. So you don't really use this part of Dalton's law here. You're just going to use the sum of the partial pressures equals the total. Is the only part of Dalton's law that you really use. Okay, so those are the two types of Dalton's law. I'm happy to do an example if you have one for me later. Questions before I move on? Yes?
So in with over water in two,
Yeah.
with the volume, you have to be given the volume.
The volume would be the total volume, is the question. Whatever the total volume, it's not the partial volume, it would be the total volume at which you're collecting the gas, and that would be a given. It'd be rare to have you solve for that. I guess that's possible. Yeah, more typically a given. Anything else? Yes?
We were taught in my discussion that we subtracted the pressure of the H2O from the total pressure of the gas and from the total to find it. Does that work?
That's the same thing. So, yes, another way to write the first one on the right-hand side, the partial pressure of the gas is P total minus partial pressure of the water. Or, I just wrote P total as the sum of the partial pressures. Either would be the same thing. Okay? All right. Cool. Let's look at an overview of the gases now. We've done a lot of little pieces. I'm going to look at this. This is on page 48 of the reader if you have it. So a couple parts, different parts of what we learned. We did kinetic theory. This is where we have the root mean square velocity, the kinetic energy, and Graham's law all fit within there. The other thing you'd want to know is the 5 assumptions. You don't have that down, get the 5 assumptions. And initially, after we did the 5 assumptions, we came with 3 formulas, what helped us get a formula for pressure. So we looked at the collision frequency and the momentum of the impulse, and put those together to make the pressure. So I'd look at that part or review it if you haven't already. And then I already mentioned the velocities and stuff like that. For the gas laws, there's the ideal gas law, I saw that several times. There's the combined gas law, or Boyle's, Charles, all that stuff. So most people have seen this in high school. For the ideal gas law, remember it can be paired with a density or a molar mass calculation. Those would be the same sort of calculation, but just paired with the ideal gas law. Law of combining volumes is the volume ratio, and then we just did Dalton's law. So those are all the gas laws that go together. Gas properties, it's just all conceptual. This is the first section of the chapter. And then real gases, we covered the compressibility factor, which is the way to tell if it's ideal gas. An ideal gas has a compressibility factor that's near what number? 1, meaning, just look at the chapter. But PV over nRT, or ask me later about that. The other thing about real gases is to see where the error happens. So I have a whole list in the reader. I mentioned a couple here earlier about there's pressure corrections, temperature corrections, etc. So that's the overview of how I think of the gases. There's really a couple calculations. There's the plug and chugs, and then there's the gas laws. The gas laws are less plug and chug sort of formulas. All this is plug and chug, root mean square velocity, kinetic energy. These are, if you're not seeing a change, then it's probably the ideal gas law. If you see something changing from state 1 to state 2, it's the combined gas law or related. If it's stoichiometry, it's the law of combined volumes. And Dalton's law is when you have a mixture of a couple different gases. Okay. I'm going fast. You need to get home to watch TV. Okay. We did gas law. Gas overview. Let's do some chapter 7, which is the electron chapter, or in the textbook that's chapter 12. Where do I want to start here? Let's start with this. Okay. I want a small counting number. Who can give me a counting number? 4 and 2. Too slow for the rest of you said other numbers. Be faster next time. Okay, so this is the Rydberg equation. It'll be given on the exam. The Rydberg constant will be given as well. So it was 2 and 4. Which number do you want to be first, 2 or 4? 2. Okay. So we picked changing from the second orbit to the fourth orbit. Okay? All right. So we typically want to calculate that energy. That's the Rydberg constant, 2.179 times 10 to the minus 18 joules. Well, before I do this, if I'm going from the second to the fourth orbit, am I putting in energy or removing energy? Putting in. So am I expecting a positive or negative answer? Positive. If you didn't know that, now you know. Okay? So I'm going to get a positive answer. I didn't calculate this, but it's a number, joules. Okay. Now, there could be a couple additional calculations that you could do with this. Here are some examples. I could have you find the frequency. Remember that h nu equals delta E. Oh, by the way, this would be a positive number. That means it is absorbed. I mean, the energy is going into the system to make the electron jump. Or you can rewrite this form hc over lambda. So the common variables we'd have you solve for are nu, or frequency, and lambda. They'd be pretty classic ones to solve for. So for example, let's try lambda. If I had you find lambda, that would just be hc over the change in energy. H is 6.626 times 10 to the minus 34 joule seconds. That's given on the exam. And C is 2.9979 times 10 to the 8th meters per second. That's given on the exam. All divided by whatever you get for the change in energy up above. So whatever this number was, that would go right there. If I get a negative energy up above, which means energy is released, does that mean I get a negative wavelength? No, you would just take the absolute value of the energy. The negative sign just tells, or positive, tells you the direction of energy flow, but it's not carried through in future calculations. So you just make the energy always a positive when you do other calculations. So I could also ask you for the frequency as well. Here, just an example for the wavelength. Again, plug and chug, that's it. Yeah. Top right. This here? This one. That's the speed of light c. That's given on the back of the exam. H is Planck's constant, given on the back of the exam. Yeah? Yeah, sometimes you'll have to show me if you're thinking of something in particular afterwards. But if you want to color, typically what I'm going to do is give you the wavelength. I don't know if I have one handy, but I would give it in the exam. I don't know, it might take me a while to find one, but you'd have a little chart, electromagnetic spectrum chart. Yes?
Is there some cases where we have to find the nanometers? Like if you ask us to...
Yeah, I could ask you to convert. So wavelength would come out in what units, everybody? No, wavelength would not come out in nanometers. Meters. And you would just convert to nanometers if I requested that. So you just want to check what units is he asking for. And I already made the exam and I'm pretty specific. Okay, so just read the question and you should be okay. I can't find an example of what I'm talking about as far as electromagnetic spectrum, but you'll see it on practice exams occasionally. So if you want the color, you have to read off that spectrum. All right, that's it with that one. Let's see, let's do drawing. Drawing, that'll kind of combo with quantum numbers a little bit. Okay, so I could have you draw any s, p, or d orbital. Yeah?
What about the
For the Rydberg equation? So There is technically another variable in there, the z squared, which is just the atomic number. Capital Z from early on in the class was the atomic number. We're doing everything for one electron or hydrogen. And so Z for hydrogen is 1. So 1 squared is 1. So I haven't been talking about it in this chapter, but when we go to the next chapter, the periodic table section, we'll talk about it more. We'll try other elements in the same equation. Yeah, so but for this, it's pretty much going to be, Z will be 1 if you ever encounter that for exam 2. What was F2? Drawing, right? S, P, and D orbitals. So let's try a couple. I could ask you to draw 3PZ. That sounds fun. How about, I don't know, 4DXZ orbital. So I'd have you draw these. Would it be unusual? So what you would do is say, okay, I see the axis there. It's the Z-axis. So let's call it the Z-axis. I know a p orbital looks like a 2-leaf clover. So it looks something like that. Then I want to know the number of nodes in this orbital. That is what? Yeah, n minus 1, so 2. One of the orbitals, or one of the nodes, sorry, of this orbital is right here. That's called what? Angular node. Angular, it looks linear or planar. Okay, the other one, people kind of shouted out already, looks circular, and that's called a radial node. Okay, so 2 nodes. Every p orbital will have how many angular nodes? 1. Every s orbital has how many angular nodes? 0. Every d orbital has how many angular nodes? 2. If there's any additional nodes on top of the angular node, then they're radial. Okay, so let's try the next one. That's it for the first one. Yeah?
You said every D has 2 angular nodes. How would you do it
Correct.
for the Z squared? You know how to say
Yeah, I wouldn't have you draw that because I don't trust to understand what you're talking about, but it's kind of a conical shaped diagonal through the donut. You could just look on Google, but I wouldn't ask you because, yeah, it's just going to look too crazy if you try to draw it. Yeah. I would just ask you about the other 4 of the 5, as far as nodes. Or if I asked you to do the dz squared, I wouldn't have you draw the nodes. Yeah, it looks weird. There, maybe somebody has, yeah. Have fun trying to draw that. Okay. So here, you see x and z, so draw the xz axis. Like that. And it's a 4-leaf clover. Because they're not squared, I gave you the little memory device to remember that when it's not squared, it's off axis or between the axes. So we're going to draw a 4-leaf clover or a 4-petaled flower. Like that. Remember the d orbitals, except for one, looks like a 4-leaf clover. Okay. This has, now let's go like this, 2 built in. It is born with this joy. It has 2 angular nodes right there. Okay, they are the axis itself. Okay, how many total nodes are here? Yeah, nodes is 4 minus 1 or 3. So there's 1 additional node over the 2 angular. And it's radial. It would just be a circle. And that's the radial node. So total of 3. And I just expect you to be able to draw stuff like that. Yes? Does it matter? You mean, could I have labeled the vertical one X? Yeah, that's fine. You could have even drawn it come out of the page if you want to, or craziness like that. But the TA wouldn't know what the heck you're doing, so we'd probably mark you down, because that looks crazy. Okay, so just make it as simple as possible. Yes? Say it again? Shading. You can do the shading. I'm not going to grade it unless you do it wrong. Okay, so you can only lose points from doing the shading. But we'll look like this. Let's do green. Because I can't have you try shading and then you do it wrong. I technically can't give you it, you know? So it switches at nodes. So it look like that for this one, or here. And at the node it switches different phases. So it looks something like that. Yes?
as long as you alternate, it doesn't matter where you start.
Yeah, as long as you alternate, it doesn't matter where you start, as far as which one is shaded first. Do you have to label the nodes? Yes. If I'm asking you to draw something, I will almost most definitely 100% ask you about the nodes. Yes. Okay, so you don't have to shade on exam 1 or 2 if you don't want to, but somebody asked me, so there we go. It will be a big deal on the final, though. No, you will not get extra credit. Nice try. Okay. All right, that was drawing. Just make sure you can draw stuff like this. Let's talk about quantum numbers, because those are related. Quantum numbers. There's a couple types of problems. Let me go through some of the types of problems. So one is, let's say I give you n, l, m sub l, m sub s. Let's say I gave you this as -3, and this one I gave you as 6. So I want you to fill in all the blanks. So I'm asking for all possible quantum numbers here. So if you want all possible, what's m sub s? That's the easiest one. You got it. Okay, a lot of you are rocking on that one. Plus minus half is not related to any of the others. Okay, L, what's the largest it could be? 5, that's right. It can't be 6, can't be equal or larger, so it could be smaller. Okay, could it be 4? Yes. Could it be 3? Yes. 2? Okay, there's a fight now. It can't be 2, I agree. But now normally it could be, but m sub l is given. So it's restricted by m sub l. A 5, for example, do the first one, would give an m sub l between -5 up to +5. Okay, so it would have a -3 in there. A 4, the next one, would go from -4 up to +4. The -3 would be in there as well. For 3, it would go from -3 up to +3. But if we had a 2, it would only go from -2 up to +2. So the -3 in the m sub l wouldn't be included. Yeah? Yeah? What would you give on exam? I would write 3, 4, 5. Yeah. Okay? So that's one type of question. The other type of question is, let's say n is 3. Give me all possible, what's the total number of electrons that can be in this orbit? So total, there's a little different ways you could write it, like what's the total number of spin up electrons or total number of spin down, but let's just do total for this one. So in this case, what you would do is you'd say, well, let's write all the values of L. Now m sub L is not given, so now I have freedom to write all the L values. And then for each L, I'm going to write m sub L down here. So if L is 0, m sub L is 0. If L is 1, this is 0 or plus or minus 1. And if L is 2, this is 0 plus or minus 1 and plus or minus 2. So I'm writing all the values of m sub L. Now, these represent the number of orbitals. Number of orbitals. So the s orbital has 1 orbital. The p has 3, and the d, L equals 2, has 5. Okay, so what's the total number of orbitals I have right now? 5 plus 3 plus 1, right? So 9? 9? Okay, how many electrons would I have? That's 9 orbitals. So number of electrons? 18, it's twice that amount. 9 are spin up and 9 are spin down, or for a total of 18. 2 electrons per orbital. So the correct answer would be 18. That's a total number of electrons. Okay. Another type of question. Let's say I had, I don't know, carbon, 1s2, 2s2, 2p2. Okay, let's say I have carbon. There's a couple questions I could ask about this. I could say, how many electrons are in this first orbit, first of all? 2. I want all 4 of each of their quantum numbers. Okay, so I could ask for all 4 quantum numbers of that one. So let's zoom in here. I'll get a different color. We'll zoom in. This really is one s orbitals, one spin up and one spin down, right? So for the first one, the one on the left-hand side, that one, what's N? 1. It's a 1s. What's L? 0, because it's s. What's M sub L? 0, because L is 0. And what's M sub s? It's pointed up, so it's plus 1/2. Let's try the other one. What's N? 1, because it's a 1s. L? 0, because of s. M sub L? 0, because L is 0. And then M sub s? Negative 1/2. These 4 quantum numbers are not the same for each electron because of what rule? The Pauli exclusion principle. They can't be the same. All right, so that's a type of question that we could ask about quantum numbers. So I'm kind of running out of possible questions here. Another possible question is to say, how many unpaired electrons are in carbon? How many unpaired electrons are in carbon? What do you think? He said 2, you're correct. If you have paired electrons, it'd be 4. 4 have pairs, or partner, a spin up and spin down. These 2 and the 2p are unpaired. The 2 and the 2p stay unpaired because of what rule? Hund's, H-U-N-D, Hund's rule tells you that they stay unpaired until you fill up singly, and then it doubles after that. Okay, I can't think, I'm sure there might be another way to ask quantum number questions, but this is the gist of it. Okay, that's a lot of them. All right, next, if there's no questions? Yes? These cannot be the same according to the Pauli exclusion principle. In fact, all of these would not have the same 4 quantum numbers according to Pauli. Hund's rule says that is this, and the other concept you learned here is the Aufbau process, which is just putting in electrons. It's called the Aufbau process. Okay, next. Some questions? Yeah. Almost there, d orbitals. We might finish. Let's see. D orbital exceptions. Let's talk about d orbital exceptions when doing electron configurations. So E config d orbital exceptions. 1. Okay. Well. Our periodic tables have been stolen. Okay? That's where we keep them, if you wondered. Okay? So rule number 1, or exception number 1, has to do with the 4th and the 9th column of the transition metals. So that's the chromium column and the copper column of the periodic tables. It would say that, for example, silver fills the S's halfway. And that's true in both of these columns. So the previous noble gas is krypton. What do I write next after krypton? Some S. What S? 5s, 1, and then what's the next number? 4d 10. Yeah. So I'll write it in a different color. Normal, okay, this is an exception. Normally, you would expect this to be krypton 5s2 4d9. You normally expect that, but that's not what happens. This is one of the exceptions, where it half fills the S's and fills the D's. That's because fill shells and half-filled shells are more stable. So you see both a filled and a half-filled shell, that's more happy. Okay, number 2 is for transition metal cations, you lose the S before D. So, for example, silver might be this, but silver plus would be 4D10. You lose the S first. Silver 2 plus would be Kr 4D9, etc. Normally, if you don't even know what's normal, normally you would expect the following to happen. For silver plus 1, you expect Kr and then 5S1 4D9. So you expect the D, whatever you filled last, to disappear first. Or for the second one, you'd expect this to be Kr and then 5S1 4D8. So you fill the D's last, so you take it off. That's normal, but not with a transition metal cation, any transition metal. So the normal is not correct. It's what happens everywhere else except in this scenario. Okay, the last, any questions there? Yes?
The second rule is only for the fourth and ninth, or for the entire system?
The first exception?
The second exception.
Second exception is for all transition metals. Second exception for all transition metals. Yeah. Okay. Last thing was shielding. What is that? That's when you have, let's say you have a nucleus here. Around the nucleus you have the core electrons, and around the core electrons you have the valence electrons. So the outermost electrons are called the valence electrons. The inner ones are called the core electrons. The nucleus, say, might have, I'll write this in purple, let's say there's 1, 2, 3 protons. So Z for this would be 3. Or what element is this? Lithium. If there's 3 protons, Z equals 3. Lithium has the atomic number of 3. The core electrons see the true Z. So they can tell that there's actually 3 protons, or they can tell, hey, this is lithium. I'll put lithium here. But the valence electrons are shielded, meaning there's so many core electrons in the way, they can't tell that there's 3 protons in the nucleus. So we talk about a Z effective when something's shielding. For example, they might think there's 2. So it thinks there's only 2, or it could be 2.5, anything less than 3, really. And that would be the Z effective for the valence electrons. They're shielded, meaning they're blocked from the core electrons from seeing all the protons or feeling the full effect of all the protons in the nucleus. So that's shielding. How does that affect us practically? If you imagine, I'll just draw a periodic table as a rectangle here. Imagine that's a periodic table. If you go to the left and down on the periodic table, shielding increases. So shielding increases to the left and down on the periodic table. Meaning fluorine is not very shielded, oxygen is more, nitrogen is more, etc. Francium, radium, around there on the bottom left will be the most shielded. So because shielding blocks the valence electrons from seeing all the protons, they're less attached to the middle. Because they're less attached to the middle, it makes the radius bigger when the shielding is bigger. So basically, if shielding goes up, radius goes up. So that means shielding and radius, R, goes up as we go to the left and down. Meaning, fluorine is the smallest. Oxygen's bigger, nitrogen's bigger than that, carbon's bigger than that, francium would be the largest, etc. So, a very common question would be to give you, say, 2 elements, and I'll have you tell me which one's larger. You just have to see which one's more left and down on the periodic table. That's it. And it follows the concept of shielding. At the end of the periodic table chapter, we're going to have several physical characteristics in this that you'll be able to tell, oh, this one has a larger this or that, or smaller this or that, but that will be saved for the final. So we're going from, on exam 2, oxidizing reducing agents, all the way up to radius. Everything in between. One question, then I'll dismiss people who want to go, and we'll do specific questions. Yeah. Oh, okay, yeah. I don't think I mentioned this in class on Thursday, but the ones that are more closer to the nucleus are better at shielding, or they're less shielded, meaning they're not blocked by anything. So an S orbital is very spherical. It's close to the nucleus, so it's the one that does the blocking and is not blocked by others. Or the way we would say that grammatically, it's the best at shielding. Yeah, it'd be the best at shielding. I guess that'd be the easiest way to say it. Okay? The F, it has a lot of lobes on the outside, so it has more electrons in the valence area. So it's more shielded. Yeah. All right, I'm going to pause right there. We finished our general topics. You can stay in your seats if you want to hang out for specific questions. But if you're like, no, I got to see what people are wearing, get home, go do your thing, and yeah, I'll see you in class on Tuesday. So I'll give you about a minute to get out of here, and I'll start with everybody.